Hello, good afternoon. Welcome to this webinar. We are going to wait 1 minute to start. Good afternoon. I'm Alejandra Lorenzo and I'm going to be the speaker of this webinar, the IDAL allocation based on the SAI ARP4754A. And during this webinar you can leave your doubts and questions in the chat, and after the webinar we will have some time to answer your questions. Okay, what are we going to speak today? First, I will do an introduction of the SAI ARP4754A. Then we will go in deep of what is the development assurance level, the definition of IDAL and FDAL, and then the assessment process. After that, we will explain some practical examples that we face here in GMG Solutions under our experience. And then we will summarize everything that we spoke in the conclusions. Okay, what is the scope? The scope is to do a short introduction of ARP4754A and the functional hazard assessment and preliminary system aircraft safety assessment. Then we will explain the guidelines and methods for conducting development assurance level allocations to functions and items for civil aircraft and systems. After that, we will discuss practical examples for FDAL IDAL allocations that we face in our day-by-day work. We will start with a little bit of history. So everything started in 1975 when the DO 160 appears and define environmental test. After that, the DO 178 appears to test and validate the requirement for software, and different amendment of the DO was during the time. In 1996, the ARP4761 and ARP4754 appears. Here, when these guidelines appears, is where the IDAL allocation process were defined. After that, the DO 254 was developed to validate the requirements and for complex hardware. And then the CS 23, 25, 20, all the CS were developed in 2003. And so on. Different amendment of the rules were produced after that. Okay, the relationship between these rules are here. So first, we have the safety assessment, the ARP4761. In this guideline, what is defined is what are the safety documents that you need to develop for certify a civil aircraft. Then, to go to the architecture and to evaluate the architecture, the requirements, and the criticality level of this architecture, we have the system development, the ARP4754A. In this guideline, we have two DOs. Well, in the guideline, we set all the requirements for software and complex hardware. And then, with the DOs, the software DO178C and for hardware DO254, we validate all these requirements with the test. So we need to differentiate what is a standard and what is a guideline. The standards are the DOs, for software and hardware, and especially for the hardware for complex hardware. And then the guidelines are the ARP4761, ARP4754. That the second one was mandatory in 2012. And we are waiting for, maybe in October, we will have a new amendment of the ARP4761. So we will come the 4761A. Well, what is the ARP4751A? The title is Certification Consideration for Highly Integrated or Complex Aircraft Systems. So in this guideline, we will evaluate the complex and highly integrated systems, and the FDAL and IDAL is one thing to evaluate these complex systems. What is a highly integrated system? Is a system that performs multiple aircraft level functions, and complex is a system whose safety cannot be shown solely by tests and whose logic is difficult to comprehend without the analytical tools. Okay. Okay. To know where all the IDAL and FDAL allocation need to be performed, in what time of the product life is performed, we have this B diagram. This is a typical B diagram. So we have in the left hand the aircraft requirement and system allocation, item allocation. When we are defining all the requirements and we are defining the software, the architecture of our system or our item, we develop the fault trees, the FHAs, the PSSA. So there is where we have to assign the FDAL and IDAL. It's better to do it in an early state of your product, because then you will have the requirement set and will be easier in the future for the development. So in the right hand, during the integration, is where you are going to validate all these requirements. Okay, what is DAL, Development Assurance Levels? So the DAL is a measure of the rigor applied to the development process of an aircraft system functions and items that have an adverse safety effect in their exposing service. So what is that? Is that when you are developing an item or a system, so you will set some requirements from the safety point of view. So these requirements you need to be sure that you are going to comply in these requirements. So the DAL set all the requirements that you need to comply to make sure that this item is not going to fail. Then we have the FDAL-IDAL assignment is a top-down process. So first you will have your function of your system, then you will have sub-functions, and then the items. So in the FHA you will evaluate the criticality of these functions, and you will assign a severity. So based on this severity, then you are going to start to assign the FDALs, and so on, and after the IDALs. Okay, so as I said before, we start with FHA, but the FDAL and IDAL is part of the PSSA or the PASA, the Preliminary System or Aircraft Safety Assessment. So you will have the FHA with all the failure conditions and functions, the operational requirements, and a proposed architecture. So you are going to evaluate this architecture and everything. So in the PSSA, you will evaluate that, and you will derive safety requirements, and you will assign the FDAL and IDALs. Okay, some definition that you need to know before we start. So a functional failure set, what is that? is the smallest group of basic events which combined cause the top event to occur. So if you have two soft functions, so to fail the top function, you need maybe two functions to fail. Because these two will be a functional failure set. You will see later, don't worry. Then we have, okay, the IDAL. I put here two examples, but now with the drones and everything is changing. So the severity, first you have the severity, and with the catastrophic, hazardous, minor and non-safety effect. So for aircraft, civil aircraft or rotorcraft, you will have for catastrophic an A hazardous a B, major C, and so on. And then for the CS lures or lures that are drones, the DAL is changed, and it's B, C, D, D. And there is another one for VTOL now is different and different configuration. So you need to make sure what is your case, in which is your case. So to start the DAL, we will start with the FDAL, but first we need to have the FHA. So we have here an example of the FHA. Well, you have a function, provide thrust. This function has two failure conditions. Function not provided when required, if function provided incorrectly. So one is classified as catastrophic and the other one is classified as a hazardous. So the one that is classified as a catastrophic need to comply an FDAL A and the hazardous B. Well, I didn't say it, but I will do the example of a civil or aircraft or rotorcraft. So it will be in this example, in the first one. So yes, the catastrophic will be A and the hazardous will be B. Then that we have assigned the FDAL in the failure conditions, we go to the IDAL. For the IDAL, we need to know more things. It's a little bit more tricky. So first, the process is the same. To assign an IDAL is the same that assign an FDAL. But you need to go, instead of functions, to items. That's the point. That's it. Then, from now I will say that the functional function set is equivalent to the fault tree minimal cut set. So I will speak for minimal cut set because in the fault trees we get the minimal cut set. You will see later. Then another point that make a lot of discussions in the companies, I think, that is the IDAL has not a direct correlation with the numerical probabilities. So if you have an item that needs to be an IDAL A, the failure rate does not need to be 1 minus 9. So there is no direct correlation. You need to assign the qualitative requirements that are the IDALs and then the numerical requirements that are the target probability. So there are two different separate methods and they are not correlated. Okay, another thing that the ARP4754 define is simple hardware. What is a simple hardware? Well, something that we can assume is from a simple hardware, you always can assign an IDAL A. But what is a simple hardware? So, I don't know if this picture is clear, but is that if you have a simple hardware is like the white box, a complex hardware is the black box. So you have an output, and if you have an input, you know what is going to happen inside, and you will have this output. So the failure, you will know what is going to happen all the time, and if you have a failure, you expect what is going to happen. But in the black box, you don't know what happened. You have an input and then an output, but has an different behavior inside, and you don't know what is. So a simple hardware is an item that can be fully tested and analyzed. Okay, a theoretical example for the FDAL is we have a failure condition that is catastrophic and another one that is hazardous. For the first case, okay, the failure condition is we have a function and it's an FDAL A. So to derive this ARP in different subfunctions, we need two options. The first one is that you need one member with ARP, but the other ones cannot be lower than level C, or two ARP. But be careful, because in this case, if you have two ARP, then you need to demonstrate independence. In this case, we will define what is independence. And for the hazardous, it's the same. In the first option, you need to have one member ARP or two ARP-C. But if you have two ARP-C, you need to demonstrate independence. Okay, that is complex, a little bit tricky for software. For hardware, it's a little bit easier to demonstrate that, but for software is tricky. So for demonstrate independence, we need to comply 3 criteria: redundancy, isolation, and no command modes. The redundancy is that you have multiple independent items to accomplish a given function. For example, you need to give power to an aircraft, so you will have batteries and generators. Okay, you have redundancy, fine. But then you need to check if this redundancy is independent. Well, you need to comply all of them. Then we go to the next one. What is isolation or partitioning? So the items need to be physically segregated. These cases are, for example, the PDUs. You have a primary PDU and then a backup PDU. So these need to be physically aggregated. You can have in a same box both the primary and the backup. No, does not comply with independence. And then the last one is no command modes. One error cannot produce a failure in 2 different items. What is that? For example, you have this PDU and you are feeding the PDU with batteries, with one battery, but you are feeding the primary and the backup. So if you lose the battery, you will lose both. So you have a command mode, because one error will make fail the other 2. And there's different cases, because maybe if you have the same batteries, then you need maybe you need to choose 2 different manufacturers, or development process, or bases, or so on. Okay, now that we set all the concepts, I hope that you follow me and you can understand all the concepts. We will go through the practical examples that will make it clear. So some symbology that you need to know, because now we are going to evaluate two different failure conditions, and these failure conditions, we will have the fault trees, and then you need to know what is to interpret the fault trees. So this is the first one, that is an AND gate. The AND gate is if you have under the AND gate 2 basic events, both basic events need to occur to make the AND gate occurs. For the OR gate is if you have 2 basic events, when one basic event occurs, then the OR gate will occur. Then we have the basic event. If we have this basic event in different places of the fault tree, we will have a repeated basic event. Then we have as well an undeveloped event. This is if you have an item but you don't know the behavior, because it's at the beginning of the architecture that happened at the beginning of the design. So you don't know properly what is the behavior of this item. Then you can put an undeveloped event. Then if you have an item that this item will fail, but you won't be able to notice. So this is a dormant event, repeated event, because it's blue. And then the last one, the box with the red highlight, is a minimal cassette highlighted. You will see it in the fault trees. Okay, the first example. We have, this is an example for an environmental control system for a CS2023. So we have a failure condition that is unprotected overheating condition, and this failure condition is classified as a hazardous. So the top event of the fault tree, that is here, this OR gate, is the top event, so need to comply with an FDAL B. So first we need to get the minimal cut set. So what is the minimal combination of this basic event to make this top gate to occur. These are the minimal cut sets. So if valve 1 and valve 2 fails, we can check here 1 and 1, this will occur. Well, we have lost switch 2, switch 1 and ECU, then the top gate occur because we have here the ECU and here both switches. But we highlight later. So first we will evaluate this case, that is the ECU one. So we have the AND gate is failure in the valves, and that needs to be an FDAL B, because we are, and that is B, and as it up OR gate, that is B, and that needs to be B. So here we have failure in the valve B, so the combinations can be valve 1 and valve 2 can be CC if we demonstrate independence, as I defined before, BD or DB. Three of them are fine. That was the easy one. Then we go next. What happened? Yes, we have here the ECU and the switches. So this will occur, and this needs to be IDAL B. Okay, so now we have a function that is control of the valve. The control of the valve is lost, and then we have a failure on the passive control and failure of the active control. So we have two subfunctions. One function, two subfunctions. Then we need this. We have these items. We have switches, and the switches can be assumed as simple hardware. So it's easy because then we have everything is A. So for this gate, we have everything is fine because we have A. But then if we go to the ECU to be compliant with that one, we have the ECU can be B, C, D, but in this case D is not acceptable because that is C. So if that is D is not acceptable, you are not compliant with this OR gate. Then in this case, in this combination with BD, we have B, C, D, it's fine. Or the ECU can be any of them. And then in the other combination, DB, in the ECU can be only B, because CD is not compliant with this failure, this OR gate. So that is the next one. Okay, now we go to another failure condition. I will like to explain another failure condition, because then I will summarize all the conclusion that I am explaining. Okay, we are still in the environmental control system of an aircraft or a civil aircraft. So the failure condition is loss of air conditioning supply. In this case, this failure condition is classified as major. So major needs to be FDAL C. Okay, let's go. Well, that one, the minimal cut sets are the gate valve is a single point of failure. So when we have a single point of failure, that means that the IDAL needs to be the same that the FDAL. So the gate valve is automatically IDAL C, because the top gate is C. So we are fine. The mufflers, in this case, we can consider them as simple hardware, so are going to be IDAL A. So we are again with the same valves, because it's the same system, different failure conditions, but we have two items involved in different functions. Okay, that is the minimal cut set. So we have here the both valve, and we need to evaluate this both valve for this AND gate. So in this case, so here we are, that is directly in the OR gate with the basic event. Oh no, here. So here the loss of cabin and cockpit line is classified as C. So in the OR gates can be DD, EC, and CE. So these basic events are under these gates. So to be acceptable, we need to have It's like a single point of failure inside the OR gate. So if this OR gate is D, the basic event will be D, because it's a single point of failure inside this OR gate. And that's for all of them. So the combinations are like this, and here it's going to be the same. Okay, we are going to summarize everything that I explained during these examples. So the first one thing, that when you evaluate different failure conditions inside a system, you need to then cross-check these failure conditions, because you will have more than one item involved in different failure conditions. So maybe one failure condition is more restrictive than the other ones. So once that you have evaluate each failure condition separately, you need to evaluate them together to cross-check that. So I will do this example. So that is what we did before. We have the first failure condition with B, C, D. The ECU was B, the conclusion were B, C, D. And the valves, that were the possible combination of these valves. Then we have the next failure condition, that was the gate valve was one minimal cut set, is single point of failure, fine, C. But then we have again the valves. Okay, what happened? The valves, any of the combination that we put in the valve for this failure condition is acceptable, because you need in here, for this failure condition, for this failure condition, we have CC or BD or DB. So you cannot have DD, because you are not complying in any of them, and you cannot be CE, because here there is no E, and here is the same. So any of these combinations that we analyze in this failure condition is possible due to the first failure condition that we analyze. So the summary will be that. For this item, we have the gate valve should be at least IDAL C. The ECU should be at least IDAL D. And for the valves, you have a possibility. If valve 1 is IDAL B, valve 2 need to be at least IDAL D, or vice versa. Another possibility is both valves IDAL C. Okay, and that is the example. I hope that you could follow this example. It's a lot of work, but when you are doing it, you need to be really careful and checking everything, and with all the minimal catches and the fault trees, and assign everything, and then do the cross check. So I know it's a lot of work, but it's really interesting, because you arrive to really interesting conclusions and can help to the design team, the IDALs and FDALs. So the conclusions. We know that the ARP4754A is mandatory for a civil certification process of an aircraft since 2012. Then for a complex hardware, we need to follow the DO 254 to develop a complex hardware. The requirements, we will set the requirements in the ARP, but we will follow this line, this DO, to test the complex hardware and verify the requirements. Then we go to the software, and it's the same. The we have DO 178C for the software. Now we know that for simple hardware, that is easy, that a simple hardware is a fully testable and analyzable item. We can assume an IDAL A from according with the ARP4754A. So it's fine. Then another conclusion is that when you are analyzing and you are deriving an IDAL and FDAL requirements for the design team, it's good and it's worth to analyze these things in the early stages of the project, because that will help you to select your suppliers and will save time and money in the future, because if you need to do changes in the architecture, do it to these assignments, because you are not compliant with these assignments, then you will have to change the architecture, and if you are in the future, then you will spend more time and money to do these changes. So it's really worth to start this analysis at the beginning of a project. Then something that make a lot of discussion, under our experience, make a lot of discussions in the companies, is that the IDAL is not directly correlated with numerical probabilities, as I said. So you have a qualitative requirement that are the IDAL, and numerical requirements that are the numerical probabilities. So that is separate two different methods to verify something, and you need to do both. It's not only one. Then, something interesting that is a little bit more tricky is to verify isolation, diversity, and independence criteria. The independence criteria is something tricky to demonstrate, and for software is more tricky. And then the data allocation is used in the first stage of the PSSA, but you need to develop anyway the safety documentation with quantitative analysis. With this quantitative analysis, you need to use reliability data from suppliers, MP, NPRD, EPRD, or NIL handbook, or whatever rules that you will follow. So that is the webinar. I'm going to check if you have any questions, and I will try to answer the questions. Yes, I will wait some minutes if you have questions and you want to write something, and then we will start to answer the questions. I hope that you enjoyed the webinar. Okay, I have the first question. Okay, for the drones operation, the question, I will read the question. Yeah. Do you have any information of possible adaptation of this standard for a specific category of drone operations? Okay, these standards are, the ARP4754A are, these are for drones, for aircrafts, or whatever you are developing, because you have to be careful in which stage you are. It's as I said, for example, for catastrophic, in the aircraft, civil aircraft, you need to comply an A. But for drones, if it's your case, you need to comply a B for the catastrophic. but if I'm for the VTOL that we are working on another project that are VTOL, the catastrophic is a C. So the assignment is the same. The point is what is the criticality and what is the level of requirement that you need to achieve. So you need to know in which part you are, and then you will follow the same approach. It's not the same, obviously, to need a catastrophic with a C than a catastrophic with an A, but will be the rule of, that is the rule, the standard is the same. I will show you, wait. Here is what I said here. Here, okay. You need a rule, you have a rule, the C is 23, 24, well, 24 no, 23, 25, 27 or 29, so you have this criteria, or for the CS lures or lures that are drones, you have this criteria, B, C, D, D, that is less restrictive, and if you go to the VTOL, is CCC, so it's less restrictive even though. So you need to know in what is your case. And once that you know the case, then you do the FDAL and IDAL assessment process. Okay, thank you very much for your time. Thank you very much for your time. I hope that you enjoyed the presentation and that help you in your work, in your day-by-day work. And if you have any comments, any questions in the future that you would like to know, yes, you can write to us and we will be really happy to answer your questions or to help you to anything that you need.